there exists, so what we have here is that there exists an n in S, so n has to be an element of S, such that, okay, uh, such that P of n is true. In other words, such that n to the power of 200 is an element of S. Okay? So this here, okay, this here is the predicate, and this over here is the quantification of the predicate. Okay, so here's our quantified predicate. So let's assess this to see whether it's true or false. Okay, so can we find an n in S such that n to the power of 200 is actually an element of S? And in particular, if we consider, so don't forget, S is the set that contains the values, as I say it was there a moment ago, contains the values 1, 4, 7, 3, and 9. So you can see that when n is equal to 1, we have that 1 to the power of 200. Well, 1 to the power of 200 is equal to 1, which is an element of S. So there does exist an n in S for which this statement is true. So what we now know is that this particular quantified predicate, okay, this quantified predicate is true. So we want to negate this quantified predicate. Just keep in mind that the universal quantification goes to there exists, right? And there exists is taken to universal quantification, right? And also the predicate, okay, itself is negated, so the predicate is negated. So there's two things to do. We flip the quantifiers and we negate the statement itself. So this is going to become there exists becomes for each and every n that's an element of S, we must have that n to the power of 200, and we need to negate this so it's not an element of S. So let's assess this. So this statement is saying for all of the n's that are in S, we have n to the 200 is not in S. Okay? So for them all, so let's take 1. So 1, when n is 1, we have 1 to the power of 200 is 1, and 1 is in S, so this statement is actually false. Right? So it says it's true for them all, and we just found an example of where it's not true. Okay, so this statement here must be false. Okay, so that statement is clearly false. Right? Let's have a look at another example. Let's say we have something like part 3. Okay, so let's say we have something like for every n that is a member of S, right? We have minus n is also a member of S. Okay, so the quantified piece is this piece here that's saying for every n that is a member of S, and the predicate itself is that minus n is a member of S. So this says for every n that's an element of S, so we have for each and every n that's an element of S, well, we must have that minus n is an element of S. This is the quantified predicate, right? So this is now our quantified predicate. And is this quantified predicate true or false? Well, it's saying that for every single n that's in S, that this thing must be true, that minus n must be an element of S. Okay? And once again, if we just look at 1, okay, when n is 1, well, the negation of 1 minus this would then, the statement would be saying that minus 1 is an element of S, which is clearly not the case. So we found a counterexample. This says for them all. What about 4? Okay, so when we look at 4, okay, well, 4 is an element of S, but minus 4 is not an S. Yeah, okay. So we can actually see that this particular quantified predicate, okay, is false. What about its negation? And don't forget, for each and every is taken to there exists is taken to for each and every, and the predicate piece, the predicate component, is negated. Okay, so what we have here now is when we negate this particular quantified predicate, for each and every goes to there exists. So there exists an n that's an element of S such that minus n is not an element of S. Okay? So this is the negated quantified